Welcome back. Our next presenter is Max van Amerongen, otherwise known as Maxploit. His talk is titled Actions Speak Browser Than Words, Exploiting End Days for Fun and Profit. Thank you so much, Matt, for supporting the Red Team Village, for supporting Grey Hat. And without any further ado, the floor is yours. Take it away.
All right. Welcome to my talk on exploiting browser end days. Now, I've said here that it's for fun and profit, but that's kind of a misnomer because this entire process causes nothing but pain and despair. So as all good talks start, who am I? Well, I'm Max, or better known as Maxploit. I'm a security researcher at F-Secure, which means I get to do a lot of really cool things, and I live all the way over in rainy England. I'm also on the F-Secure Labs Pwn to Own team. I got to participate in the Tokyo contest last year, and I'll be there in a few days again, but this time in a remote capacity. My main passions are browsers and routers, and that might seem like opposite ends of the spectrum, but I have seen a few JavaScript interpreters in embedded devices, and it's never a pretty sight. So what am I going to be talking about today? Well, recently I analyzed and wrote exploits for two different browser vulnerabilities, one in Internet Explorer and one in Firefox, so these are their stories. I'm going to go over the vulnerabilities, how I began looking at them and how I ended up exploiting them, and hopefully give some sorts of lessons that should be taken away from the entire process. I'm also going to avoid using too many code screenshots, and by that I mean giant blocks of C++ or assembly without any context, because it kind of defeats the purpose of the talk if the only people that are going to understand what I'm showing are the people who already have a very intimate knowledge of these systems. I've also left out a couple of bits of information because these vulnerabilities can get a little bit heavy for a single talk. But if you're interested in filling in some gaps, please do read my F-Secure Labs blog post. And, always send me a Twitter message if you've got questions. Finally, this is an exciting tale in which I probably upset an APC by mocking them. So why would you bother writing end-day exploits when you could just fuzz for 0 days? Well, fuzzing and exploit development are often seen by people as part of the same thing, and while that's true, they're in fact two very different skill sets. It's easy to assume that every crash in a browser is exploitable, but that's really just not the case. And if you understand the code base and the ways in which you can manipulate it, you can figure out the ways in which you can go from some crashes into an exploit. It's also really useful to note that if you know how to trigger crashes in a particular environment, you can actually use this with your own fuzzers by structuring test cases in different ways. And this could lead you to you finding different bugs that you may not have otherwise caught because they weren't really doing anything noticeable. Another reason is that it's actually just really fun to write exploits for bugs. Most of you know how there's really no better feeling than getting a shell, and that's just way better when you write these exploits yourself. And finally, it's great to just invest time into this, even if you don't do it for a job. I'm sure many of you have come across a vulnerability in a target during an engagement where there have been no public exploits for it. And exploit development gives you the chance to get a bit creative and DIY with it. So as I said, there were two bugs here. There's an Internet Explorer bug and a Firefox bug. Now the Internet Explorer bug was a use after free, and the Firefox bug was a JIT bug. So how did this whole thing start? Well, I was scrolling through Twitter and I saw a tweet about this bug called CVE 2020-0674, which was supposedly used in the wild back in January. Now, since I have an unrequited love of browsers, I thought I'd have a look into it despite not really spending any time on JScript internals previously. So I knew there was a bug in JScript somewhere, but at this point the engine was pretty much a black box for me. And now, for those who haven't really heard of JScript DLL before, it's the legacy JavaScript engine that was used in old versions of Internet Explorer. However, for compatibility reasons, which is the only reason anyone would ever use Internet Explorer these days, websites can actually cause it to be loaded instead of the newer engine, which is called JScript 9.dll. And this can be done by doing some weird HTML magic. So the Microsoft page, of course, just had the usual copy and paste spiel about there being some vulnerability in some place that does some things, but there's no real information there. So I turned to the source of the discovery, which is Kihu360, who had written a really great blog post on this attack, and they'd called it the double star attack because it was targeting two different browsers. Now, this blog post actually contained a small code snippet which showed the vulnerability in the array.prototype.sort function. Now, I have Google translated the comment here for people who aren't super fluent in Mandarin, and it basically says that the variables a and b in the function free and comparator are not tracked by the garbage collector. So I did what any researcher would do in this sort of situation, and I dove in deep and hoped for the best. So the first thing I did was I got both versions of JScript from the Microsoft Update Catalog, which is a really great resource if you want to do patch diffing for Microsoft things. Then I fetched the symbols. So in Binary Ninja, there's a really nice option for this, and the same with IDA. If you're using Ghidra, it's easily done if you're on Windows, but if you're on any other host OS, you're going to run into some problems. You're going to need a VM instead. So the next thing I did was differential debugging against both versions. And this is where you trace the execution of both versions to figure out what's changed. So for this, I was using the small script on the right, which is supposed to trigger the vulnerability, more or less. So the other really useful technique is called binary diffing. And there are lots of really great tools for this out there, but for IDA, the main two are Diaphora and BinDiff. And I use this in conjunction with differential debugging to figure out which of these many changes between the two DLLs were actually relevant to the execution of the function. So these two methods showed that there was a bunch of refactoring done to the JavaScript function call code, but one of the key points was the addition of a new object called scavVarList, which stands for Scavenge Variable List. And the initialization of this object calls a function called iScavengerBase link to GC, which, as you can imagine, links things to the garbage collector. So at this point, it's always good to verify your findings in some way. So for me, I set a breakpoint on the link to GC call in the scavVarList initialization, and then I skipped over it when it was reached. And this caused the vulnerability to be triggered and the target to crash, which had verified my assumptions. So I mentioned from the Q360 post a little bit about the bug. We know that it's related to the garbage collector and how it's tracking some of the arguments in the array prototype sort function call. And we know that if an object isn't being tracked, then it's going to be freed when the garbage collector is called. So let's take a quick overview of what that sort of looks like. Let's say we create an object, and with this code we've got a variable a which points to this object. If we create a second variable called b and have it point to a, then both a and b will point to the same object. Now, we always know when variables themselves are going to be within scope and when they're going out of scope. For example, if the variable is declared with let, that means it's only going to be valid for the current code block. But objects are a bit different. So say when a and b both reach the end of their scope and are removed, how do we know that the objects that they reference aren't being referenced by another variable? And this is what the garbage collector is supposed to take into account. So the JScript garbage collector is actually done in 3 stages. The first stage is the mark stage, which marks all the objects as ready to be garbage collected. The second stage is the scavenge stage, and this unmarks all objects that are referenced by variables, and then on each of these objects it will call the scavenge function. Now the scavenge function is basically used by objects to say which objects that they reference. So for example, if I had an object called dog and it had a property called name, when the scavenge function is called on this dog object, it would need to say, okay, also unmark the object that's in name because I'm still using it. Now finally, the reclaim stage will free any objects that are still marked. So let's have a look at what happens with the array prototype sort function. Well, the mark stage marks the object that's been given as an argument to the function. The scavenge stage, however, is supposed to unmark this object since it's referenced by one of the arguments. But since the argument isn't being tracked by the garbage collector, it's never unmarked. And this means that when the reclaim stage happens, this object's freed and A is left as a dangling pointer, and that's how we get our useof to free. Now, in order to actually exploit this bug, the JScript engine internals need to be at least understood a little. And like attacking any language, this kind of involves a few key things like understanding variables, object representation, heap allocation, and the garbage collection stuff. Now, you don't need to know everything, and I really can't stress this enough. A lot of people get very put off by looking at complex targets like this because of the sheer size of them. But even with a 40% understanding, you can still be quite proficient in attacking a target. And once you reach that point as well, it's a lot easier to start figuring out the parts that you don't know by looking at the parts that you do. So what do variables look like in JScript? Well, they're represented by a structure called a var, and they look like this in memory. There are three components to each var. There's the type of the variable, and that's whether it's a string, a float, or an array. There's the object pointer, which, as the name suggests, points to the object. But it's worth noting that if the var type is for an integer, then this isn't going to be a pointer. It's going to be used as inline storage for the number. Now, the next var pointer isn't always used, and it's kind of pretty irrelevant for this bug in general, so there's not really a huge amount of point going into it. Now, objects in memory come in two types. You've got natives and you've got non-natives. So natives, also known as built-ins, are programmed into the engine themselves. So this is things like regexp, date, or an array. And non-natives are those that are programmed by JavaScript, the JavaScript developer. So, for example, earlier I gave the example with the dog. That would be a non-native because it's programmed by me, the JavaScript developer. Now, we could free our variable and reallocate it with another one, but that wouldn't really do much except make variable A a different type than it was before, and that doesn't really do anything useful for us. So an alternative is to replace this entire var with something that's different and more within our control. And when objects have properties, they're stored in this structure called a vval. And this structure has a variable length because of the name str member at the bottom, which stores the property name. And this makes it a perfect choice for reallocation because we can both selectively choose the size we want it to be, and we can choose the contents using the name string. And this is something you'll see a lot in Chromium exploits as well for use after free bugs, in which the blob type is used to reallocate things for these exact same reasons. So one of the key parts of heap allocations is the GC block structure, which holds an array of up to 100 vars. Now, when the use after free happens, the variable, A, as we called it earlier, will actually point somewhere within this region. Now, we need to free this entire GC block structure and reallocate on top of it with something of equal size, but something more useful to us. And that's where the vval comes in. Now, with most JavaScript engines, if you want to trigger the garbage collector, you need to do it by creating lots of objects until the garbage collector is called. But for those of us that are lucky enough to be exploiting JScript, we've actually got a handy function which is called collect garbage, and this will run the garbage collector whenever we want it to. So at this point, we've got all the pieces we need to write the exploit for this bug. So the process is then pretty straightforward. So first thing we do is we create a large number of untracked vars, and then we use these to fill a bunch of GC block structures. And we'll store these untracked vars in an array. But now the next thing we do is we call the garbage collector, which will free all of the created objects and leave the untracked pointers in this giant free region. Next, we use reallocation, and we do this with our vval. Now you'll notice that the entire free space was not reallocated. And the reason for this is that the allocator that's used for allocating vvals is called pvalloc, and it actually just allocates a large chunk of space so that when we create more properties, the allocator doesn't have to go through the process of allocating more memory. It just returns a pointer to the next free space. And this is actually going to be quite crucial for us later. So the property name itself that we're going to be using here is broken down into several parts. There's 8 bytes of padding, and we use this in order to align where our fake vars are going to be with where the real vars are expected to be in the GC block. The next part is the fake var, which we've written as a string, and you'll notice that the numbers are represented in little endian byte order because that's how they're expected to be in memory. And the third part is that we're using this fake var and we're copying it until we reach the desired size that will make pvalloc allocate a similar size to GCblock. Now, next we want to iterate over our untracked vars and check which of them are numbers and also have the value 1, 2, 3, 4. And you might be wondering why we're even bothering checking the type if we just want to know the value. And the reason for that is, let's say an untracked var now points to junk data. Well, then if the junk data for the in the var type part makes it think that it's an object, and there's going to be junk data in the object pointer, when it tries to dereference that value, it's just going to crash because it's not a real memory address. So this is why we check the var type first, so that we don't cause this sort of bad value to be dereferenced. So at this point, we've managed to cause a type confusion in which a property name string has been treated as a var. And we can now reallocate the object with the property name to replace the value of our chosen untracked var with varying fake vars. So currently, because of how ASLR works, we don't know where in memory our objects are going to be located. So there are two choices here for info leaks, but my favorite one, and the one that I'm going to use, is to leak the next property pointer of the vval. And this is actually a technique that was that I saw Ivan Fratrick using. And if any of you want to kind of do even more deep diving into JScript, pretty much just read anything that guy's written because it's all fantastic work. So let's take another look at the vval. Here we see that there's a hash, a name length, and a next property pointer. And the hash is used to quickly compare the name str without having to do a byte by byte comparison. For example, if I create an object with a property name that's 1,000 characters long, you can imagine that each time I'm trying to compare, it's going to take a really long time. So in that instance, it's much faster just to use the hash value. And then we have the name length, which specifies the length of the name str. And the next prop pointer is the pointer to the next vval. So, for example, if I have an object with properties A and B, the next prop pointer in the vval of A is going to point to the vval for B. Now, the hash and the name length are both 4 bytes, which means that they're placed next to each other to make a single 8-byte value. However, because the var type value is only expected to be 4 bytes, this means that only the hash is used for the var type. So, let's say that we create we have an untracked var and it's pointing to the hash value of a vval. The object pointer of the location would then be at the same point as the next prop pointer. So if we have the value of the hash ending up at the value 5, which is the var type for a 64-bit float, then we could read the next prop pointer in line as a float value. And this would reveal the memory address of part of the pvalloc region. Now the hash algorithm itself is really simple. We can actually just control it by using a single 1-character name. So in this instance, the property name with just the value 0x05 would be the one that generates the hash for 5. So let's start where we were. We create our vval structure, which causes an allocation of the on top of the GC block, and the property name here will also be used to align the vval so that the hash of this second vval will be treated as the var type by an untracked pointer. Next, we create 2 more properties. The first will have to be a single character name, so that its hash is the 0x05, and the second we create is so that the 0x05's property its vval will have a valid next prop pointer. And next we iterate over our untracked pointers until we get a float value. And since we know that the only float value we have is going to be the next prop pointer, that's what we use. So from here we can calculate the offset to the untracked var because it's always going to be static. And this will give us the address of our untracked var. Now, since we now know where in memory we are, we can construct 2 important primitives, and that's the read primitive and the adderof primitive. Now read is of course used to read arbitrary memory locations, and adderov is used to get the address of objects. Now with most other exploits you'd probably need a write primitive, but for this one I didn't need it. So the read primitive is actually pretty straightforward. You just need to know how strings work. Take this JavaScript line. We create a variable str which is assigned the string abc. Now str is of course going to be represented by a var structure, and the var type for a string is 8. Now the object points directly to the string, and the 4 bytes before our actual string is used for the length of the string. And this layout's called a BSTR, and it's actually used in a lot of things that Microsoft develop. You'll notice that the size of this string says that it's 6 characters long, but ABC is just 3 characters. And this is down to the fact that JavaScript strings are UTF-16 instead of UTF-8, which means that we have 2 bytes per character instead of 1. However, the BSTR structure actually measures things in bytes. So we can use the str.charactCodeAt to get the character ASCII value at the start of the location. So in other words, we'd read our first byte. And all we need to do now is point the string pointer to the target address we want to read, correct? Well, turns out that this doesn't actually work because we can't just set the object pointer to the target address, because the BSTR's size could end up being null, which means that characterCodeAt 0 wouldn't actually return anything except undefined, because the string is seen as having no length. But what we can do is use the length to read memory. So let's look at our memory layout again. Say we change the string pointer to 4 bytes ahead of the target address, so that the D word at the target address is now in the length part of the BSTR. We can read its value by then fetching the length of the string. But really what we're doing here is we're getting the string size divided by 2 because of the conversion rate, and divided by 2 just means shifting right by 1 bit. So instead we'll add 2 bytes to the target address. Then we shift along 7 more bits so that we've aligned a full byte instead of just a single bit. And then we shift along another 8 bits so that our target byte is in the least significant bits of the value. And then we can filter out our byte by using the bitwise AND operator. Now that might have been a bit confusing to look at, so here's a different way of breaking it down. So here we have our target address, OX7FF-OB14A. Now let's say the byte we want to read is OX04. If we set the string pointer to that location, it'll look like this in memory. This means that the value we want, in this case 4, is not currently in the BSTR length. So we add 2 bytes to the target address, which means that the address for our string pointer is now OX7FF-OB14C. Now when we get the length of the string, we're really getting it divided by 2 again because of the conversion from UTF-8 to UTF-16. So str.length gives us this, and our aim is to get the 4 that we had originally. Now as you see, our numbers are looking a little bit different to what we were expecting them to be, and that's because the bytes are currently misaligned. So the first thing we do is shift along by 7 more bits so that we've shifted a total of 8 bits. And now we've shifted 8 more bits so that we move the 4 to the least significant bits of the value. And finally, we use the bitwise AND operator to get the last byte. And that's how you put together a really hacky and awful read primitive for JScript. So next, we just need an address of primitive. And it turns out to be really simple, thanks to our old friend, the vval. Now you see at the top of the vval, there is a var. And the purpose of this is because properties are supposed to point to things. So this var is used to hold the value of the property. And since we know where this vval structure is going to be in memory thanks to our info leak, we can just assign the target object that we want the address of to this property. And then we use our read primitive to read the object pointer of the var. Now finally we've got to get some code execution going, and this actually turns out to be really simple again. First we create a fake C++ object with a fake vtable. Then we create a fake var that points to this fake object, and we make sure that the var type is 0x81. Now finally we call the type of on this object. And it turns out that vars with the type 0x81 will actually call a function from their vtable in order to get the type string. Now we can point this anywhere we want because we control the vtable. But where do we jump to? Well, since DEP is enabled, I went with a different choice, and that was to do a stack pivot in MSVCRT. Now, a stack pivot is basically just a gadget that moves a controlled value into the stack pointer, and this allows us to move the stack elsewhere. So in this case, the controlled value was actually in a register because of how the vtable was being accessed, and since I controlled the vtable, I now controlled the stack pointer. So this technique is really useful if you've got a limited amount of space on the stack, or you've got a single gadget like this scenario, and you want to kind of move the stack elsewhere with more gadgets. So in this case, the chosen location for me was a string I'd created with a bunch of ROP gadgets in it. So from here, the ROP chain executes and a shell is born. So a week after releasing the exploit, my mates from work had kind of egged me on to make a better payload. So I went with the obvious choice, which was the desktop goose, and I called it Dark Honk. And this was because the vulnerability was attributed to Dark Hotel, which is probably not my smartest move, and I'm probably going to regret it one day. But yeah, you got to enjoy the little things. So let's move on to the next part, the Firefox JIT bug. This section is a little less intense, partly because there are quite a lot of resources already out there on Firefox, and also because I have talked quite a long time about JScript. So this all began back in January when I saw some articles about a big scary vulnerability. So the first thing I did was I updated my local Gecko dev repo, and I did a quick search for the bug ID, and this led me to a particular commit with the date Jan 1st, 1970. And this commit had showed that there were two files that were changed. There was the aliasanalysis.cpp and the mir.h. And these are both part of IronMonkey, which is the JIT compiler for SpiderMonkey. And for those that don't know, SpiderMonkey is the JavaScript engine that's in Firefox. Now, the most important change here was in mir.h, which used the getAliasSet function. It was no longer overridden by these two nodes. And this was actually something that sounded very familiar. So it turns out it was actually a variant of a bug that was used in Pwn2Own 2019 by Team Fluoracetate. And basically the JIT compiler wasn't taking into account the fact that some operations can cause side effects. And because of this, you can cause JIT to be executed without taking these changes into account. So before going on to exploitation, we should definitely cover the basics, as in what even is JIT? Well, JIT just means just-in-time compilation, and it's a technique where your browser compiles your JavaScript code to assembly, and it does this if it thinks it can speed things up. So what I mean by it thinks it can speed things up is if we've got a function which is called a hot function, so one that has been executed a lot, like 10,000 times or so, the browser will actually think that it's faster to spend a little bit of computation power compiling this function because it's so constantly used. But JIT can't just be done and then left alone. It's got to take a lot of changes into account. So take this function, for example. Every time it's run, it expects the argument obj to be both an object and have a property called x. And when this function gets compiled, it'll essentially be reduced to something like this, which gets the properties pointer and then changes the first property, which it assumes to be x, to the value 10. But what happens if I give the function an object without any properties? Well, in this case, the compiled code would no longer be valid. And because we have no properties on this object, the compiled code would just end up writing out of bounds. And this is why the JIT compiler needs to take lots of things into account and monitor for changes that could actually invalidate the code. So IronMonkey doesn't immediately end up with that representation. In fact, most of JIT compilation has nothing to do with code generation, but mostly about program analysis. And this is because if you convert a JavaScript function safely into assembly, you won't end up with any significant performance changes unless you reduce the code into only the instructions that are necessary. So we can see that the initial intermediate representation checks the i's within the bounds of the array. So to us, and it does this every time it uses it. And to us, this kind of seems a little bit redundant because we only need to check that I is going to be within the bounds of the array once because nothing is being changed between it. So once all the fancy program analysis is done, the second bounds check has been removed. But what if there was a way to cause a side effect from this assignment? And that's exactly what this bug is about. So IronMonkey works with by using different nodes to represent different basic instructions, similar to how I showed a minute ago. Now the two nodes that were changed in the fix were mStoreElementWhole and mFallibleStoreElement. And mStoreElementWhole would be if I had an array and set an element outside the bounds of it. And mFallibleStoreElement would be if I had a dense array, which is an array that's packed without any missing values, and then I set an element within the bounds of the array. But this array, this operation could fail because, for example, the array could be frozen. Now I mentioned that one of the important points was that getAliasSet was no longer overridden. And getAliasSet is used to define what effect a node can have. And if this isn't correct, it can actually cause nodes like the bounds check earlier to be eliminated. And unfortunately, this was the case for these two nodes. So how do we cause a side effect by setting an array element? Well, we can use the defineSetter function on an array in order to add a function that's triggered when an array element is set. Now, unfortunately for us, this doesn't quite work because when we do this, the mStoreElementWhole node isn't generated anymore. Instead, we get stuck with an mStoreElement node, which is just not as fun. But if we define a setter on a property, the mStoreElementWhole node is now generated. But of course, this isn't going to trigger the function. So when we JIT the function, the nodes can be kind of summarized like this. We take I, check that it's an int 32, and then we use mStoreElementWhole on the array's elements with I as an index. However, this says nothing about using the number -1. And in JavaScript, this isn't an array index. This is a property, but it's still a number, and so we'll get past the int32 check. So we can define a setter on the property -1, which will pass that int32 check and reach the mStoreElementWhole node. And this node will then trigger the function, which will print reach. But this wasn't taken into account with the getAliasSet function, so we can cause changes to occur without the JIT being invalidated. So let's take this function here. We'll create an evil array at the bottom with a setter defined on the -1 property. We'll then call the JITted function with the -1 property and the number 1. Now the JIT function creates another array called target with 3 elements. And first it uses j as an index on the target array and sets the value to 1. Then we trigger our side effect, which sets the length of the target array to 0. And finally we use j as the index again and set the value of the target array to 1. Now the initial IR is as expected. The value j is checked within the bounds, is bounds checked twice. And because the JIT compiler sees this, when we get the resultant IR, the second bounds check is removed because it doesn't think there's a need for it. But it didn't account for the setter function. which has now made the length of the target array to 0. And this means that the second array will now write out of bounds. So how do we go from an out of bounds write to code execution? Well, a common way to do this in JavaScript exploitation is to use arrays. And this is how objects and arrays are represented in memory in SpiderMonkey. So the group points to a structure which holds things like the prototype of the object, but it's also used for things like certain JIT operations like type inferencing. Now, the shape points to a structure that defines the names and indexes of properties, and the slots pointer points to the memory location in which the properties have their values. So that's how the shape and slots work together. Shape, you get the names, slots, you have the values. And finally, the elements pointer points to, well, the array elements. So if we can use our out of bounds write to overwrite the slots pointer of an object, we can point it to arbitrary memory locations and read the value by checking a property. Now, remember how in JScript we had the integers being stored in line in the object property pointer? The object pointer of the var, and that was done to save space. Well, a similar sort of thing actually happens in SpiderMonkey. Each value is stored as what's called a nan-boxed value, and this is where some of the most significant bits of the value are used to define the type of the value. So this is an integer with a value 1, this is an integer with the value 2, and this is an object pointer with the address OX1481FEB3A810. And this is actually going to be quite important for our read primitive later. So here's our target array. We can see the elements pointer points to a block of memory allocated after it with the values 1, 2, and 3. Now on our first write, we write the value 1 to the index 2, and then we call our side effect function using our evil array, and this will set the length of the target array to 0. Then when the second write happens, this is going to go out of bounds. So at the moment we're just writing to freed memory. So what we really need is to write to something useful. So for this, we're going to use 3 arrays. And the third array will need to have a property. Now we write to the target offset again so that the JIT compiler will remove the second bounds check. And now we trigger our side effect, which sets all the array lengths to 0. And then it also calls the garbage collector, and this reallocates each of these 3 arrays next to each other. Now when the out of bound write happens, we change the second array's length of its elements area to a very large value. And from here we've actually got a very stable read and write primitive, and we no longer need to use the JIT vulnerability. So all we do is we use the second array to write to the slots pointer of the third array, and then we use this third array to read and write to arbitrary addresses using the property. At least we can kind of do that. So remember how values are nan-boxed? A value like this could cause SpiderMonkey to dereference it and crash because it's not a valid address. So what we've really got here is a weak read-write primitive. And we need to find a way to make it a strong read-write primitive. And this is where typed arrays come in. So a float64 array, for example, will not use nan-boxing, but simply store the 64-bit floats in memory as is. So step 1 is to create a new float64 array. And next we get its address, avoiding the nan-boxing by reading half the value at a time. Now I kind of wanted to go more into this address of primitive, but I didn't feel like I'd have enough time to do it. But yeah, basically it's using 3 different properties to read part of the address at a time. And if you're interested in kind of knowing how it really works, do check out the F-Secure Labs blog post because it goes into way more detail. So we use our weak primitive to write to the target address of the buffer pointer. And finally, we use the float64 array to read and write exact values to the target address. So finally, we need to use our primitives to get code execution. Now, we can't do the thing that we do with Chromium and read and write shellcode to a WASM region because there are no read, write, execute mappings in SpiderMonkey. And this means that you've unfortunately got to write your shellcode as a series of floats, and you do this in a JITted function. Now, you got to do this all the while avoiding constant folding, which will basically remove anything that it thinks is a duplicate or not relevant to the execution of the function. And that's not really a fun experience. Now, you'll notice that the first value is the float equivalent of OX41414141. And the reason for this is so that we can find our shellcode in the JIT region. And once we do that, we can update the JITted function's JIT pointer to point to that location. So this means that instead of jumping to the start of the function, which will treat these values as just numbers, we jump to the values themselves, and they'll be treated as shellcode because this area is mapped as readable and executable. So yeah, when the sandbox is disabled on Firefox, you can pop calc. But this vulnerability was used in the wild in a real world attack. So how did they do it with the sandbox being enabled? Well, that JScript bug from earlier was actually used again. And it was done from inside the Firefox sandbox. And this actually exploited the fact that WPAD, or Web Proxy Auto Discovery Protocol, can execute JavaScript scripts to configure proxies. And Google Project Zero did a really incredible write-up of this a few years back. So this isn't exactly a new technique, but it shows how even bugs in old, very ancient JavaScript engines can still be used in real-world attacks. So I guess just some final notes. Both of these vulnerabilities were variants. The JScript bug was a variant of the bug that Microsoft had tried and failed to patch multiple times. I think they've been trying for about 3 years to patch this one. And the Firefox bug was a variant of a pwn-to-own bug. So the takeaway point is really, if you want some 0 days, just do some variant analysis on new bugs. I've actually seen this a couple of times in the Chromium bug tracker, where someone has reported a bug and then a few months later, someone reports a bug that looks exactly the same. Now, while there's lots of work that's involved in this entire process, it's actually quite a lot of fun to write the exploits. So I do recommend people give it a shot. And of course, don't be afraid of the super big scary targets. Once you start with n days, you'll feel a lot more comfortable finding 0 days. All right. Thank you for watching this presentation, and I'm here to answer any questions you might have, or you can just message me questions on Twitter if you prefer doing that.